Okay, next up, I'd like to find out how many orbitals are there in the third shell and show the orbital diagram for nitrogen, sulfur, and bromine. So, the answer to this question lies in your quantum numbers. And so you have n, which is called the principal quantum number, and n can take any value from 1 to really infinity if you wanted it to. L is called the angular momentum quantum number, and L can take any value from 0 all the way until n-1 is the highest value that it can take. ML is called the magnetic quantum number, and it can take any value from negative L all the way including 0 to positive L. MS is the spin quantum number, and it can take values of +1/2 and -1/2. So this comes into play, like for example, where I have helium, so it has 2 electrons. In my diagram, that means I have 1s2, and so that means 1s2, and it would be my 1s. This 1 is n, this s is equal to L. So it's when L is equal to 0. Remember, if n is 1, L can only be equal to 0. And then the number of orbitals I have would be dictated by the magnetic quantum number. And so L is 0, that means ML can only be 0. So the label for this one would be ML is equal to 0. If I have 3p as another example, this means that my n is 3, my p is my L quantum number, so L, and it's specifically when L is equal to 1. And when L is equal to 1, ML can take values from negative L, so -1, 0, and 1. And that's actually how I label these three, -1, 0, 1, and then the spin would be +1/2, -1/2, +1/2, -1/2, positive, negative. And so these 4 quantum numbers just dictate your labeling of that energy diagram, and that the energy will be dictated by the quantum numbers. And so if I have n is equal to 3, how many L values can I have? So L will tell me how many orbitals I can have. And so L would be equal to 0, 1, or 2. 0 is S. And for S, when L is equal to 0, ML can only be equal to 0. And so you only have 1 orbital. When L is 1, recall ML can be -1, 0, or 1. So I'll have 3 orbitals here. And lastly, when L is 2, ML can be -2, -1, 0, 1, and 2. And so I have 5 orbitals here. And so namely, that would be your 3s, your 3p, and your 3d. So the 5 that I discussed, when L is equal to 2, this is the d orbitals. When L is equal to 1, these are the p orbitals, they are 3. And when L is equal to 0, that is the s orbitals, and they are 1. And so that will all add up to 9 orbitals in the third shell. Okay, next up, I'd like to draw an orbital diagram for nitrogen, sulfur, and bromine. And so I can begin by just writing out their electron configurations. So just quickly look at the periodic table. Nitrogen is going to be 1s2, 2s2, 2p3. So 1s2, 2s2, 2p3. The next one they ask for is sulfur. So sulfur is right here. So again, just count it out. 1s2, 2s2, 2p6, 3s2, 3p4. And lastly, I believe the last one is bromine. And bromine is right here. And so its short configuration would be AR in square brackets, and then I'll only count along this line. but I'm just going to count from the beginning so I can have the entire diagram. 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And so in actuality, this 3d10 is supposed to be here, but just because of the way that the periodic table is built, when we write out our structure according to the periodic table, this is what you get. But bromine technically has 7 valence electron, these 2 and these 5. So now I begin with nitrogen's diagram. I will have energy going up that way. I begin with my 1s2, and then I will have my 2s2, and then lastly I have 2p3. So 1, 2, 3. Next up I do sulfur. So again, I'll have my energy going up that way. I begin with my 1s, and then I have 2s, and then 2p, and then 3s, and then 3p. And that's going to be it for this one. And then lastly, I will have bromine. So again, I have my energy going up that way. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but as I mentioned, this 3d should technically come before it. The reasoning why is just because the energy spacing between 4s and 3d shrinks as you go down the periodic table, and so at a certain point they actually cross each other, and 3d now goes under the 4s, and that actually happens around scandium, and so that's why bromine only has 7 valence electrons. But of course we can't tell you that with the periodic table, because that would place this group here, and that isn't technically correct, because the crossing happens at scandium. And so because there's no way to notate that crossing in the periodic table, it isn't necessarily included. And so we're going to have 3p6 and then 3d10, and then your 4s2, and then your 4p5. And so the orbitals have different energies depending on their s and n values. That's going to be because of the way that multiple electrons interact with each other, because of electron repulsion and shielding, which can also be called screening. And so in the solution given here, that isn't accounted for. It's given in the hydrogen-like fashion where all of the orbitals are of the same energy. For hydrogen, that is true because you have one electron. One electron can't shield itself, but for elements where you have many electrons like this, you will have shielding, and these will not all be degenerate or at the same energy. And so this is going to be more accurate than what you have here.